Hello, and welcome to the TI Precision Lab series on current sense amplifiers. My name is Chuck Udigboy, and I'm a product marketing engineer in the current and position sensing product line. In this video, we will introduce the different types of amplifiers used for current sensing, and the strengths and weaknesses of each. In today's training, I will introduce the basic concept of direct current sensing. This method is based on Ohm's law, where load currents generates a voltage across the sense element, typically a shunt resistor. This shunt voltage, or sense voltage, is measured to determine the current level. It is an invasive measurement method where power is dissipated by the shunt resistor. The sense voltage across the shunt resistor is small, typically in the millivolt range, so it must be amplified and signal conditioned to be processed by systems downstream of the current sensing circuits. I will review the pros and cons of various implementations so that you can choose the best method for your application. Before we can look at the various circuit options, I need to introduce some basic concepts that will help you better understand the application. The first concept is input common mode voltage, VCM. Common mode voltage is defined as the average voltage of the two input pins of a differential amplifier, as shown in the figure. Depending on your measurement technique and application requirements, your amplifier may be required to either handle a very low or a very high common mode voltage. The next concept is low side or high side sensing. A low side implementation has the shunt resistor or shunt placed between the system load and ground. This results in the common mode voltage being essentially 0 volts. This type of configuration is usually simple and inexpensive to design. However, there are two disadvantages. First, it disturbs the ground seen by the load. And second, it prevents the ability to detect load shorts to ground. A high side implementation has the shunt resistor placed between the supply voltage and the load, resulting in the common mode voltage being essentially equal to the bus voltage. This allows for the system to not have any ground disturbance, and to identify ground shorts. But depending on the system voltage, the system may require an amplifier with very high common mode voltage capability. Direct current sensing typically uses a differential input amplifier to gain up the small sense voltage. There are four main types of differential amplifiers that are used for current measurements: operational amplifiers, or op-amps for short, instrumentation amplifiers, difference amplifiers, and current sense amplifiers, also known as current shunt monitors. Each of these has their own pros and cons, which we will now discuss. Op-amps offer the most basic implementation and typically are used in lower accuracy, low-cost applications. However, the cost savings are offset if high-accuracy external components are used to increase precision. Because the common mode voltage of an op-amp is limited to its supply voltage, these are best suited for low-side measurements. If implemented with a single-ended input to the op-amp, any parasitic impedances on the printed circuit board, PCB, between our shunts and ground will create errors due to additional voltage drop. Difference amplifiers are designed to convert small differential signals to large single-ended signals. The typical voltage drop across our shunts is small, so as not to add to the overall system load. Therefore, the difference amplifier architecture is well suited to most current sensing applications. Because the input voltage is differential, errors due to PCB parasitics are removed. These devices have a resistor divider network at the inputs, which allows large common mode voltages and enables high side or low side measurements. However, the resistor network can also load the system, introducing errors if not handled carefully. Instrumentation amplifiers are a combination of a difference amplifier with a buffer stage on each of the inputs. This very large input impedance enables the measuring of very small currents. However, the architecture limits the use to the application where the common mode voltage is within the supply voltage range. Like a difference amplifier, the differential input voltage removes errors due to PCB parasitics. Current sense amplifiers, also called current shunt amplifiers or current shunt monitors, are specialized amplifiers with a unique input stage that enables the common mode voltage to be much higher than the supply voltage. In addition, they integrate a high-precision, low-drift gain network that maximizes measurement accuracy. The input structure is such that limits the use cases where the I shunt is greater than tens of microamps. Direct current sensing is a simpler to implement and lower cost method of current sensing than indirect magnetic methods. And current sense amplifiers offer the most comprehensive set of features to maximize current measurement performance for the widest range of applications. The table shown on this slide summarizes the 4 types of amplifiers we have discussed in this video. That concludes this video. Thank you for watching. Please try the quiz to check your understanding of the content. For more information and videos on current sense amplifiers, please visit ti.com/currentsense.